Welcome to solverfy.
In this question, we have to prove that for nearly normal incidents, the value of R parallel is equal to n minus 1 by n plus 1 into 1 minus theta I square by n, where theta I is the angle of incidence, n is the refractive index of the transmitted medium, and the incident medium of light, we can take it as air medium having refractive index 1. So following previous problem, for nearly normal incidence, we got for nearly normal incidence, we got minus of sine theta I minus theta t by sine of theta I plus theta t, can be written as n minus 1 by n plus 1 whole multiplied by 1 plus theta I square by n. So this is what we got in the previous problem. So let's say this is my equation number 1. Now for small angle of incidence, we can expand cos theta, or let's say cos theta I plus theta t, where theta I plus theta t angle is going to be a very small angle for nearly normal incidence. In that case, we can write it as 1 minus theta I minus theta t whole square by 2 plus theta I minus theta t whole to the power 4 by factorial 4. Actually this is 2 factorial, and this way it will continue up to infinity. And similarly, we can write cos of theta I minus theta t, we can write it as 1 minus theta I, this one will be cos theta I plus theta t, all this will be plus theta t, and this is will be minus theta I minus theta t whole to the power 2 by factorial 2 plus theta I minus theta t whole to the power 4 by factorial 4 minus, it will continue up to infinity. So if we just follow the trend of previous problem, then we can write over here that cos of theta I plus theta t by cos of theta I minus theta t, that is going to be approximately equal to 1 minus 2 theta I square by n, where n we can write approximately equal to as theta I by theta t for nearly normal incidence of the incident light. Okay, so now we can use the formula for R parallel. So we can write, as we know that R parallel is equal to tan of theta I minus theta t by tan of theta I plus theta t, which we can write as sine of theta I minus theta t by sine of theta I plus theta t into cos of theta I plus theta t by cos of theta I minus theta t. So by doing further simplification of this, we will get R perpendicular. Okay, now let's find R perpendicular for theta I nearly equal to 0, that is for nearly normal incidence. So that is going to be equal to, we can put the values of sine theta I minus theta t by sine theta I plus theta t, which is going to be equal to n minus 1 by n plus 1 into 1 plus theta I square by n, following previous problem, into the value of cos theta I plus theta t by cos theta minus theta t, which we got over here as equal to 1 minus 2 theta I square by n. So you can put that 1 minus 2 theta I square by n. So the further simplification of this will give us equal 1 minus 1 by n plus 1 into 1 minus 2 theta I square by n plus theta I square by n minus, sorry, minus this is going to be, yeah, minus 2 theta I to the power 4 by n square. Now again, as theta I is a small quantity for nearly normal incidence, so we can neglect the higher order terms of theta. That means we can neglect this last term, or we can equate this to equal to 0. So we can write that R parallel for nearly normal incidence will be equal to n minus 1 by n plus 1 into 1 minus theta I square by n. So this is the proof for this equation, which is true for nearly normal incidence of the incident light. So this is the answer for the question.